What do all these things have in common? And as you look at these 5 pictures I have up, you probably guess that there's some sort of motion being depicted. In the first picture over here are the crayons. You can see a bullet that just went through each crayon. You have a runner, a skateboarder, looks like a dog with his head out the window of a car, and a ballerina. And turns out motion, although we talk about it quite frequently in everyday life, turns out that it's more complicated to explain motion than it might first appear. And we're starting our unit on motion right now, specifically speed, velocity, and acceleration. And we're going to be starting a lab, or you're doing a lab right now, that I'm going to talk about. So this is the front page of your lab, and you can see it says lab, speed, velocity, acceleration. I actually don't have any acceleration problems in here, but I give you page numbers to help you. And it's set up sort of like Cornell notes to some extent. Your job is to sort of self-explore using your textbook in your mind and some other resources what some of these topics are in a deeper level, hopefully, than we've thought about before in here. And it just starts out with, what is speed? And you can just write your answer over here. You can use your textbook if you need help with that. You write down the formula for calculating speed here, and then here's just a simple math problem where you calculate speed. Of course, you know how to use these. You write the formula here, you list your variables down here, and you show your work with units over here. And why don't I solve this one with you? So let me move this over a little bit. So formula, of course, is speed is equal to distance over time. And you just list the variables down here. Speed, distance, and time. Okay, just reposition that. I hope that shows up on the screen better. You don't know the speed in the story problem, but you know the distance is equal to 70 meters. And you know the time is equal to 1.5 seconds. And over here you just show your work. So you go speed is equal to 70 meters divided by 1.5 seconds. And then you just take 70 divided by 1.5, and whatever answer you get in your calculator, you write that in here. And of course your answer needs units. So your units are right here, meters per second, or meters divided by seconds. So you divide those on your calculator, put your answer right here with units of meters per second. And then you're going to apply that to a real thing. So I ask you to get a piece of paper here, drop it horizontally so it falls slowly from 1.5 meters high. If you can't measure 1.5 meters at home, drop it from the top of your head and then time it to the ground and just assume that that was 1.5 meters. And you just put the formula we just used here, you list your variables, you show your work here. Then you're going to change the piece of paper over here to crumpled, and crumpled meaning like in a little ball, and it should fall faster. And you repeat all that right here. You should get a faster speed here than you did over here. And just have a think about question here. And then at the bottom, I'm asking you to graph what that might look like. And it says to use different colors here for your graph for 2 different lines. If you don't have those colors, you can just change the key on your graph. But without giving too much away, the paper that was flat, do you think a line for that paper looks like this? Or do you think a line for that paper looks like this? Or do you think a line for that paper looks like this? It's what do you think on a time distance graph that would look like? And then you also are supposed to graph the other line and what you think that looks like. So if you think that's this line, maybe you think this one looks like that. I'm not giving you the answers here. I'm just asking you to think about it and try to come up with what you think it would look like. And then as you go through the lab, you're asked to discuss velocity. And most of this information, at least parts of it, can be found in a book. What's velocity? How are speed and velocity different? If you don't have the resource here, a string and a washer, anything with a string with some sort of weight attached to the end that you could spin in a circle, you could use to answer these questions here. And when you spin something in a circle, I'll just draw a little diagram. Let's say you're spinning something in a circle like this, and you're keeping it at a constant speed as it goes around. How is this an example of speed staying the same but velocity changing? And it really requires you to understand the difference between speed and velocity. So if you don't get that concept, you need to go back and reread those ideas. And page 4 of your lab is using vectors. And a vector is just an arrow that shows both a magnitude or a size in the direction of that motion. So for example, if I have two arrows like this, you can see they're both going in the same direction, but because I drew one bigger than the other, it has a bigger size or magnitude. So maybe this is, and I'm not actually, just to clarify, I'm not actually answering this question right now, I'm just explaining what a vector is. Maybe this is going 2 meters per second east, and since this one's bigger, this would be going 20 meters per second east, and those are vectors. I don't want to give too much away, so I'll just leave it at that for now. Let me get rid of these. So, let's see here. You're going to need to use your book to kind of solve those problems. There's almost an identical example in your book, and so you want to draw pictures of a bus and a person on the bus and then showing their combined velocities. And again, check out your book. It gives great examples of what that might look like. And then the last work. Sorry if that didn't come through. The last page is the A-quality work. And this does require some math. Again, I'm not going to go over the exact answer here, but I'm going to go over something that will help you get to the answer. So I'm going to shrink your last page really small because I don't want you to think I'm solving the exact problem for you. And I just want to give you an idea that might be helpful to you. Turns out that if you have one object going one direction, and since this is a vector, I'll label it 4 meters per second east. And I don't know the directions in your problem. I'm not even looking at it. So again, I'm totally making numbers up here, but I'm trying to illustrate how you might show the idea. And let's say you have another arrow or direction here, another vector, and this is showing that you're going, let's say 3 meters per second, and we'll just call this south. Well, it turns out if you're on the land, and we'll use the boat since in your problem it was a boat. Let me draw a little boat on there. Let's pretend this is the boat. Okay. So the boat's going 4 meters per second east, and for example, the water is going 3 meters per second south. Turns out if you're on the land right here, and you had a radar gun and you radared the boat with your radar, you wouldn't get either of these numbers. And because they're not going the same direction, you can't just add them, or going opposite directions, you can't just subtract them. So how can you solve it? Turns out we can use a little math, can use Pythagorean's theorem. We can combine your two directions into a triangle right here. So I'm going to draw a triangle. And turns out if we just turn this into a math problem using Pythagorean's theorem, we can figure out what this value is here. And it turns out that if I actually radared the boat, this value would be the exact speed of the boat. So how do I solve this? Well, you would just simply take, I'm going to shrink that a little bit. a squared plus b squared equals c squared. And you can let, for example, this value equal a and this value equal b, and the thing that's important is you allow this value to equal c. Okay. So I'm going to plug in my numbers. I'm going to leave off units. Technically you could include units, be better, but I'll leave off units just to keep it simple. So I'm going to plug 3 in for my a value. So I would get 3 squared plus, now I'm going to plug in 4 for my b value. 4 squared is equal to c squared. And when I do that, I get 9 plus 16 is equal to c squared. Now I can add my 9 and 16. I get 25 is equal to c squared. However, c squared is not the same as c. So what I have to do is I got to get rid of my squared. And the way I do that is I do the opposite of squaring to both sides. I take the square root of this side and I take the square root of this side. When I take the square root of this side, my squared and square root cancel and I'm left with c. So now I just take the square root of 25, which is 5, and I actually know that this side of the triangle would be equal to 5. And that actually gives me the velocity of the boat itself, is that value right there. So that's how you'd solve that problem. I've pretty much walked you through it more than I wanted to be honest. It gives you an example. It's not the exact numbers you have in your problem, but definitely helps you solve it if you needed a little help. So thank you very much for listening.